Log on, tune in, find out. Another good idea from Cambridge.
Let's start. So, Anders Hansen, originally from Norway, started his PhD at Berkeley with John Strain. After 2 years, was offered political asylum in Cambridge, where he survived the PhD with me. Went to Caltech as a von Karman Fellow, and now he's back in Cambridge as a research fellow. And he'll be talking on infinite dimensional compressed sensing.
Well, thanks very much. And does this work now? Can you hear me? Okay, very good. So, well, thanks so much to the organizers for giving me the opportunity to speak today. This is joint work with Ben Adcock, by the way. He just finished his PhD here in Cambridge in 2010 and is now in Canada. I just want to say that a lot of these things that I'm going to be talking about today, which is a slightly different approach to compressed sensing because we're going to be working with truly infinite dimensional structures. A lot of these things were actually developed while I was at Caltech, and my office was in the same corridor as Emmanuel's office, so I would frequently use his expertise, so he has certainly had quite a bit of influence on the stuff that I'm going to show you. Now, I'm going to give you a little bit of motivation for what I'm going to be talking about. And I'm going to start with the good old magnetic resonance imaging problem, namely that we need to invert the Fourier transform. So the problem with the MRI machine, or it's not really a problem, it's just a fact, that what it gives us is simply the Fourier transform of the function g, and it's really the function g that is of interest. So the reason why I picked this example is because that MRI has been very, very important. It's been an important motivation for compressed sensing. But it's another important thing, and that is that this here is really a fully infinite dimensional problem, or it's an analog problem that you may say. So a signal processing person will say, for example, that the world is analog and computer science is discrete. Now that means that if we're going to solve this problem here, which is a truly infinite dimensional problem, we actually have to make a discretization. And that is important. And this is really what this talk is about. And the fact that the world is actually analog, or in my language as a function analyst, it is infinite dimensional. We describe the world with integral operators and differential operators, but these operators live on infinite dimensional spaces. And that is really the essence of what we're going to be talking about today, because we're going to be solving infinite dimensional problems. Okay, so the problem with the MRI problem is that we see f, and we would like to get g, but the machine is only going to give us pointwise samples of f. And then the task is, how do you reconstruct your g from those pointwise samples? Now, how do we do this? And I'll show you a very basic way using a very, very well-known sampling theorem, namely the Shannon sampling theorem. So how do we do it? Well, if g is supported on some interval, say minus tt, then what we can do is that we can, if we sample at Nyquist, we can sum up, say, with sinc functions, then we can recover f. In this case here, we're going to have L2 in uniform convergence. We can also recover g here, which is the function of interest, but that's only going to be in L2 sense. And if you see here, this is really essentially the same thing as looking at the Fourier series. You know, up to a little epsilon, this is really simply the Fourier coefficients of g, and how well this approximation here that we'll use later on, how well that's going to approximate g really depends on how fast does the Fourier series converge. This is something that we know very well. Okay, so here we have a function that we're trying to reconstruct, but we cannot sample an infinite amount of information, so we take a finite amount of information, right? So we sum this up, so we take either fn here, truncate the sum, and here is gn. And this is the guy we're going to be looking at. So, let me now take a very, very simple example. I'm taking the simplest example that I can think of. I'm going to try to reconstruct G, and I do this only for educational purposes. I don't claim that this is, an important problem in MRI. I just do this to emphasize what I'm going to show you later on. So this is simply the Haar wavelet, and we're going to try to reconstruct that simply from seeing its Fourier transform. Now, there's many ways that I can think about this function. I can think about this as an uncountable amount of information. At every point here, there's a function value. But I can also think about this as a vector. I can think about this as an infinite vector with coefficients in, say, the Haar basis, right? That means that the first coefficient is going to have the value 0. That's going to be the one that corresponds to the scaling function, the constant function. The second one is going to be 1, giving us this, and the rest is going to be 0. In particular, this is a very, very sparse guy, right? And we're going to work with that later on. Okay, so what happens? I take now my Gn, as I showed you on the previous slide. I let n be 120. That means that I've actually taken twice as many samples, and I try to reconstruct. And what do you see? You see the good old phenomenon here. Well, we're trying to reconstruct from its Fourier samples, right? So you see the Gibbs phenomenon, and the problem is that you'll never get rid of that. If you take more samples, you always see these spikes here because we're simply trying to reconstruct a function which is discontinuous, and we're trying to reconstruct it from its Fourier samples, right? Very well known. And you get this here, the highly oscillatory error. And this isn't all that great. So what happens then is that there's a couple of observations we should make. The first one is that Gn does not converge uniformly to G. This is well known. And it also converges very slowly to G, simply because we're taking the Fourier series. We're approximating a discontinuous function here with its Fourier series. And then you may ask, so why on earth should we then use that? And that's a good question, and I'm going to get back to that later on. But we're going to work with this a little longer now because there's a couple of more points that I would like to make. Okay. And the reason why is the following. So what we've done, we have taken the infinite dimensional problem, inverting the Fourier transform, and what we've done is that we've simply taken a discretization, right? We take finitely many samples from this guy here. I showed you that on the previous slide. But we can interpret this in a different way. We can interpret this simply as this equation here. Y is a vector, U is a matrix, X is the unknown, where this Y vector here is going to be the vector of observations, the samples, the Fourier coefficients, if you will. And what you have here is the discrete Fourier transform, or, well, the discrete Fourier transform up to an epsilon from here. And X, the unknown, is simply a vector containing the pointwise values of the function Gn on the interval -1, 1, where the length of this vector here depends now how many samples. And this is where the discrete Fourier transform enters. That's why we talk about the discrete Fourier transform in MRI. But it's important to realize it comes from a discretization of the original infinite dimensional problem. And that is the heart of the issue we're going to be discussing. Okay, so we have talked a lot, or Emmanuel has, talked about how to do subsampling with a discrete Fourier transform. So, let's try to do some compressed sensing with it. We would like to reconstruct from subsampled samples. But the original problem that I showed you was very sparse, right? It's the Haar wavelet. It's extremely sparse. So what we could hope is that this vector here, which is the unknown here that we would like to reconstruct on the previous one, this guy here, that if I hit that with a discrete wavelet transform here, that guy is sparse. We could hope that. And if that's the case, well, maybe we can solve this problem here, the well-known L1 problem, where we're going to have the discrete Fourier transform here, and then the inverse of the wavelet transform. And what we'll do is that we're randomly going to sample some set omega here of size m, much smaller than what we're going to, the total amount of samples. And then we will hope that we can actually recover that guy here and by finding a minimizer to this problem. And hopefully we'll be able to recover that guy, and then if we have that, we can get that guy. That's the goal, all right? So let's try it. So what I've done here is that I've sampled 130 samples. That's roughly 50% of the samples, and I've reconstructed. And this is what we get. It's not all that great, it's not all that bad, but it's certainly not a perfect reconstruction of the original problem. So let's try to examine what's going on here. What would have happened if we had sampled everything here, if we saw everything? P omega here would then be identity. What would happen? This guy here then is invertible, so we would perfectly recover this guy here, right? And hence x. But the problem is x corresponds to this guy here, which is not the original guy. So we're trying to essentially reconstruct a guy which isn't the guy we're trying to get. And there's one more point. This guy here isn't actually sparse. I misled you, I have to confess. This is full. And you may have seen why, because this guy here that comes from this function here, this function here is now a C infinity function. That is not sparse in the Haar wavelet at all. So essentially what has happened is that we took an original problem, an infinite dimensional problem, and we discretized it. But during that process, we ruined the key feature of the problem, namely sparsity. So we took an original sparse problem, and we discretized it in this way, and then suddenly we lost sparsity. So the problem is that since we are essentially trying to get this guy here, which has nothing to, well, it's an approximation to the original guy, we aren't using the original property of the problem. And that leads to some questions. The first question is, if we know that the original guy that we would like to reconstruct is sparse, or that it has rapidly decaying coefficient in some basis, doesn't have to be Haar, why would we then be using this kind of discretization? Because, as we've shown, this guy here isn't actually sparse in the Haar wavelet anymore. This isn't exclusive to the Haar wavelet. Take any compactly supported wavelet. That's not going to be C infinity. So if you take this guy here then, which is C infinity, you have ruined the sparsity property again. And then the second question is, why are we using this sparsifying transformation and try to solve the optimization problem when it really doesn't help us? Because essentially we have ruined the sparsity, so this really doesn't help very much. And then the third question, which is really sort of the heart of what I'm going to be talking about, is that if we know that our original guy that we would like to get, if that has rapidly decaying coefficients or is sparse in some basis, why aren't we then trying to get those guys? Because if we can get those guys, then we can get perfect recovery. And that's sort of the essence. And here is sort of the paradox. Because if this guy here, for example, is going to have rapidly decaying coefficients in some other basis, say the Haar, that's typically when the Fourier series it's going to converge slowly, as I just showed you when you have a discontinuity. So this guy here, for example, if it's an image, well, you may use your favorite wavelet or some other functions basis. But that's exactly when this guy here is not going to be very good. So then the question is, can we do something about it? And the philosophy that I'm going to try to follow is essentially the following. If we have an infinite dimensional problem, at some point we need to discretize it. But while we're doing that, we would like to keep the original structure of the infinite dimensional problem. And by discretizing, I simply mean when you convert from the infinite dimensional case to the finite dimensional case that you can solve on a computer. And this philosophy isn't something that I just have cooked up. I mean, I should say, when I grew up, when I was a student of ARIA, I had a very strong interest in geometric integration. I was also very influenced by Jerry Marston. And it's all about structure preservation when you do discretization. So for example, if you're going to be computing, say, the Jupiter's orbit around the sun, well, there's energy preservation, right? So there's all these things that you would like to preserve, and it's the same idea here as well. You would like to preserve the original properties of the problem. Okay. So what would be the properties of the problem? Well, one thing, sparsity. Another thing is that if we think about the original problem that we had, the MRI problem, it is the Fourier transform. Now, the Fourier transform is a unitary operator. You can't really ask for a more stable operator than that. So stability is also something that we need to preserve. Okay. Now let's take a step back and enter the abstract world of Hilbert spaces. And I'm going to sort of give you the model. So what we have is a separable Hilbert space with some orthonormal set. And we have a vector. We call it x0. And the point is that we can express this guy now as this sum, and these coefficients are the ones that we're really interested in. And we would like to reconstruct x0 from some measurements. And these measurements we can think about as linear functionals. Let's call them zeta j's. And they will simply give us some complex numbers. We can think of these guys as simply giving you the Fourier coefficients, for example. That would be the one that we just discussed. It can be, for example, if you're doing tomography, it would be a line integral. So some kind of linear functional, typically an inner product with another basis. And from that, we would like to get these coefficients here. And what it gives us is essentially the following. We have the information here. This is what we see. Then there's going to be an infinite matrix here, where the matrix elements are simply given by how these linear functionals act on these functions. And here is the information we would like to get. There's one thing that I would like to emphasize, and that is that it is very rare that we have the luxury that we can actually choose these linear functionals. So for example, the MRI machine gives us the Fourier coefficients. Now we can't just say, oh, please give us something else. This is the nature of the problem. This is what nature gives us. The same thing with tomography. Then these guys here will be taking line integrals over your function. So suppose that this guy here now was invertible as an infinite matrix. Well, obviously, then there exists a mapping that takes this information here to the information we want, right? But that isn't so useful because, well, we can't sample an infinite amount of information. So we can only take some finite amount of information here, and then we're going to try to reconstruct these guys with that information. The question is then, how would you do it? And the way you can, I would say can, but a natural way would be to use what people call the finite section method. And that would be taking, say, n samples here, and then you will take an n by n section of this infinite matrix, and then try to solve a linear system and hope that that is going to give you an approximation to the, say, n first coefficients. Now, that is very dangerous business, because even if this original guy here could be invertible, you could have that the n by n section of this here is not invertible. Typically what happens also is that you can have that the n by n matrix here is invertible, but the norm of the inverse blows up as n grows. typically exponentially. Moreover, what could also happen is that this guy here is indeed invertible, but it's not convergent, meaning that if I solve the linear system and I compare those guys to the original guy, they actually don't converge. So an unstable method that doesn't converge, maybe not so good. So what does that mean? Well, the first thing is that we need to abandon the finite section method. And we need to use different tools. So what kind of tools? So before I started working on these things, I was very interested in spectral theory and how to compute spectra of infinite matrices. And you see, if we were to try to compute the spectrum of this guy here, and if you take, say, the n by n section and looked at the spectrum of that, that may have absolutely nothing to do with the spectrum of the original guy. So to solve that problem, one really had to look for other ideas. And this was how I sort of learned how to use uneven section techniques to solve that problem. And I could also use that in this case here to solve this linear system. The problem is that we need to give ourselves a little bit of wiggle room. If we say that we're going to take n samples and try to reconstruct n coefficients, that doesn't give us very much wiggle room. That gives us the finite section method. But if we say that we're going to sample, say, n samples and reconstruct k coefficients, that gives us the wiggle room we need. So what we suggest is the following. We take x, that's the guy that we're going to try to approximate our original guy, x0, that's the guy we want. And what we'll do is that we will solve this problem. Pn is going to be a projection, and when Pn acts on a vector, it takes the first n component of that vector and then throws everything away. The same thing with pk, but the whole point is that k is not equal to n, and that's important. And then you may say, well, how do you know that this has a solution? Well, if n is large enough, then this is going to have a solution, and I can define my x in this way here. What happens here is that if we look at the error between our guy that we have reconstructed as an approximation to the guy we want is now going to be bounded by 1 plus some constant, and I'll get back to the constant in a second, times the tail. And you see, if this guy here was 0, that would be the best approximation we could get if we knew, say, the k first of these beta guys. So it's sort of pseudo-optimal in a way that we get the same thing, but there's a constant here. But the important thing is that if we're interested in actually getting these betas, and if we have some control of the k, or if this was even sparse, we could recover. Moreover, what happens is that with this ckn, for a fixed k, this guy here tends to 0 as n grows. And it is possible to actually get very, very nice or explicit expressions for what the c is. In particular, it is possible to compute it. It is, of course, desirable to have pure mathematical theorems saying what it is, but even without that, it is possible to do stuff, because I can actually compute this. I'm going to show you some graphs on a couple of slides. And this kind of technique leads to what we called the generalized sampling theorem. It takes a couple of slides, so I'm just going to tell you exactly what it is before I actually continue with it. The generalized sampling theorem is a generalization of the Shannon sampling theorem. And it says that based on exactly the same amount of information, you can reconstruct, but you can reconstruct in any basis you want. That's the whole point. And that's the huge difference. So if you have rapid decaying coefficients in your favorite basis, you can still take the same sampling that you'll get with the Shannon sampling theorem and reconstruct in that other basis. That's the whole point. So say that another way, if your Fourier series converges slowly, well, change to another basis, but with the same amount of information. So what we'll do is that we'll say, okay, f is now the Fourier transform on L2 RD. We'll do that in RD now to make it complete. And we suppose now that we have some orthonormal set and they're all supported in some box. And that we'll do is that we need to have, say, one nice vector and one singly infinite matrix. That's why we need to pick some ordering from the natural numbers to the grid that is introduced by some epsilon, and the epsilon isn't going to be completely arbitrary because it has to be less than or equal to Nyquist. That's where Nyquist comes in, right? So the matrix here now is simply taking the Fourier transform of these guys and evaluate them at the grid. And then this guy here now is up to a constant and isometry. And here's the problem. Here is we have our f and we have the g, and we're interested in actually being able to reconstruct both of them from point samples of f. So g now can be written in this form with these beta j's and the phi j's, and we do exactly as I suggested on the previous slides. Here are the samples. This is what we see. Think about them as the Fourier coefficients, if you will, of g. Pointwise samples of f, exactly the same thing as you would do with the Shannon sampling theorem, but we're reconstructing now in our basis, the phi j's. So for a large enough n, this guy here is going to be invertible. I can define this guy as the solution of this linear equations, and moreover, we can define our approximations. So tilde gkn and tilde fkn now are going to be the approximations to the original g and the original f. And we have exactly the same bounds as I suggested. There's going to be 1 plus our ckn, and here's the tail. And for f, there's going to be a little contribution coming from the support of g. There's one more thing that I just want to mention. So I said we would like to preserve sparsity, and I would like to preserve stability if we have that. This guy here can be made as stable as you want. By taking this as large, you can make the norm of the inverse here as close to 1 as you want. So then the question is, what would be the number of samples versus the number of coefficients, right? I take k, the number of coefficients, and n, the number of samples. So here I have shown you what you get if the phi j's that we had in the theorems is simply the Haar wavelets. So what I have here is k, and here is n, the number of samples, and and this is for ckn less than or equal to 1. And this is computed. So if you say, look, I need to compute 200 coefficients, all right, up here, around 700 coefficients, samples do I need to see to be able to reconstruct, and then I know that the ckn in the theorem is going to be less than or equal to 1. So what you see is quite dramatic, actually, because it's better than linear, meaning that I'm not going to choose my samples n equals to k, but just a little more, and that solves the problem. And if you ask that ckn is less than or equal to 2, then you see you have a slightly different slope. So this here will be steeper, obviously, if you ask for ckn less than or equal to a smaller number. But the point is that it's going to be that n is always going to be order of k, a linear growth. All right. So that is what we call generalized sampling. Generalized sampling is essentially, oh, by the way, I just want to say how this actually becomes the Shannon sampling theorem. So if you pick these guys simply to be the exponentials, then this matrix here becomes a diagonal, well, up to a scaling factor, and then you get the classical Shannon sampling theorem. So that's just a subcase of this. Okay, so generalized sampling is essentially a linear and deterministic way of reconstructing. And what I would like to show you now is a nonlinear and probabilistic way of reconstructing. So the first question that we have is, are there other ways of approximating the problem that we're interested in? This is the problem we're interested in, right? We have information here. We would like to get these guys. And the question is, can we subsample, right? And, well, what kind of conditions do we need to be able to subsample? And this is where we're going to do infinite dimensional compressed sensing. Okay, so let's try and let's be a little naive. Let's simply try to do exactly what we would have done in the finite dimensional case. Maybe that works. Try the simplest things first. So what we'll do is simply we're going to randomly choose some finite subset and choose rows here and the samples. And then we're going to solve this infinite dimensional problem. And you may say, well, how on earth are you going to solve that? Well, I can't solve that on a computer. So let's just do this now for the thought experiment, okay? And I just want to say that infinite dimensional convex optimization isn't a new thing. It's actually quite old and well understood. There's a very, very nice book by Ivar Ekeland. It's a collection of lectures that he gave at the University of Chicago sometime in the 80s. And so this is sort of well understood. So it's not completely crazy to talk about an infinite dimensional convex problem. And now I have to, of course, tell you, well, how on earth are we going to randomly choose this set here, this set omega? I mean, it doesn't make sense to choose a finite set here from the whole set of all integers, right? So what we're going to do is that we're going to say that, well, we're not going to choose this from infinity. We're going to choose this from some finite sets. But how large should that set be? Where is the useful information that we need to sample from? That we need to understand. I'm going to get into that in a second. So if we do find a solution to 7, which is on the previous, that guy, what happens? What is the error? What's the error between that and the guy we would like to reconstruct? That's sort of the essential question. And then, if we know how large this should be, how big should that set be, then the question is, how large should M be as well? Okay, so the problem is that you cannot solve this infinite dimensional problem on a computer. So you have to do a discretization in the end, right? And that's what we're doing here. So we have randomly chosen a projection here that takes random some rows of this matrix and randomly chooses the samples here. Now what we're going to do is that we're going to truncate here on the right-hand side because this is something that we can solve. This is now a matrix. I can plug that into my solver and it's going to spit something out. We don't know what it is. Hopefully it's going to give us something. So then the question is, if we have a minimizer now of this problem here, what happens then as m grows? And we must observe the following, that m cannot be too small in this case, because what could happen is that this guy here then is not in the range of this guy here. But if you take m large enough, that will always be the case, so it does have a solution. Okay. So I'm not claiming that I'll be able to reconstruct an infinite amount of information from just some finite samples. That's insane. There must be some kind of assumptions that allows us to do this. So there's two models I'm going to consider. The first one is what I call the semi-infinite dimensional model. And the assumption is as follows. So we have this guy here, and this is the guy we would like to reconstruct. But we need to have some information about the support. And the support, by the support, I simply mean now the integers corresponding to the non-zero coefficients. So I'm going to let support of x0 simply denoted by delta. And I don't need to know where it is, but I need to have some estimate where it is, somewhere between 1 and m. And typically the size of this here is not going to be m, it's going to be much smaller. That is the kind of information we need. And with that information, then the question is, how far out, towards infinity do I actually need to sample to be able to reconstruct, right? So suppose this was 50, where is the important information that we need to sample? And then the question is, well, if we know that, if we know how large n should be, how can we subsample? How large should m be to be able to recover? And moreover, what would happen if m is actually equal to n? Will you then recover everything with probability 1? So the semi-infinite dimensional model is probably not what you'll see in the real world. What you'll see in the real world is probably something like this, that you have a vector that you would like to reconstruct, y0, which is of the following form. So you have y0 being equal to x0, and that this guy here is sparse. And we don't know the support of this guy, but we have some estimate on where it is. And then there's another guy here, which we don't know anything about. It can be full, and we don't know anything about the support, obviously, since it may have infinitely many coefficients. But we do have some knowledge about these coefficients. In particular, we have some knowledge about the L1 norm of this guy. Then we cannot hope for perfect recovery, but at least recovery and with the control over the error. So this model here is the one that's going to be most likely that you'll see. Right, so now I'm going to give you a couple of examples to show you how these things will work. So this is now the optimization problem we're going to solve, and this U matrix stem from the generalized sampling theorem here. So it's going to be simply the Fourier transform, and I'm going to pick these phi j's to be the Haar wavelets in this case here. And the samples are simply going to be the pointwise samples of f. So now let's try an example. I consider the following function. So f here now is the Fourier transform of g, and g is of the following form. Oh, I see I've used psi here and phi here. Yeah, okay. But anyway, so these guys now are the Haar wavelets, and I've taken 200 of them. But there's only 25 that are non-zero. So in particular, this guy here is very sparse, or pretty sparse. But we want to be slightly more brave. So I've added a tail to it, this guy here, which is a cosine function. And just to make it slightly more interesting, I've added a little discontinuity, which is not completely trivial. So what we have here is essentially something which is sparse plus a tail. And we're going to try to recover f here simply by taking pointwise samples and see how well we can do, right? So there are three things I would like to compare. It's the classical Shannon sampling theorem, it's the generalized sampling theorem that I showed you, and third one, infinite dimensional compressed sensing. So let's start with the classical Shannon sampling theorem. Okay, we sum up the pointwise samples of f with sinc functions. And what I'm going to do is that I'm going to take exactly the same amount of information. That's important when we compare this. So the two alternatives are as follows. I'll compute my f tilde nk, and what I'll do is that we'll sample n samples and reconstruct k coefficients in the way that I suggested before via the generalized sampling theorem. And then what we'll do is then sum up with these coefficients that we computed, and then now take the Fourier transform of the Haar wavelets. So that's the generalized sampling way. This is a linear reconstruction. And then here we do infinite dimensional compressed sensing. And that means that we have taken n is exactly the same thing here. we are taking the same amount of information, but now I'm subsampling. I'm subsampling from exactly the same amount of information. So I subsample m here, small m, and I reconstruct capital M coefficients. And that guy here is different from that guy here. And I just want to make the point that, you see, if we knew all these coefficients, we actually had to have infinitely many of them, simply due to the fact that I've added this tail here, and there's no way that you can express this cosine function here with just finitely many Haar wavelets. So this is a truly infinite dimensional problem. Okay, so now I'm going to show you the errors. So what you see here, this is the error corresponding to the classical Shannon sampling theorem. And the reason why is simply that the sink expansion converges extremely slowly. So the error here is 1.5. With exactly the same amount of information, you can reconstruct this tilde f and k, and what you get here is 10 to the minus 5. So with the same amount of information you can reconstruct, but the error is now improved with a factor which is somewhere between 10,000 and 100,000. Simply because we have reconstructed in a completely different basis, where the convergence is much faster. And then you see here, this is the infinite dimensional compressed sensing. I subsample from exactly the same amount of information. But what happens is here I've taken only 230 samples. That's 38% of the total amount. And I still get the same error. So you can, by subsampling, but choosing a completely different basis, you improve the results with a factor somewhere between 10 and 100,000, and you only take 38% of the samples. So here's a table that supports this. I've taken slightly more samples just to see, and the problem with the classical Shannon sampling theorem, and it converges very slowly. The other one, you get pretty nice errors, and of course the reason why this happens is because we are reconstructing in a different basis, and that basis is much more suited for these functions. Okay. So now we need some theory to support what we're doing. So here's the problem. We have some information where the support of the function is located, somewhere between 1 and m. And then from that information, we need to understand where do we have to sample from? How large out do we need to sample? And this is given exactly by these guys here. These guys will tell us how large should n be as a function of m. And these guys can actually be simplified much more, but they're not sharp then. But it is important to emphasize that for a fixed m here, I can let this quantity here become as small as I want by taking n as large. And the same thing with this guy here. And then the condition on m, this guy here now, is close to what you see in finite dimensions. There's log factors here. There's the good old incoherence parameter. There's some universal constant here, and then the size of the support. And if we satisfy these conditions here, you'll be able to get perfect recovery with probability exceeding 1 minus epsilon by solving this problem here. But you see, now this is actually, now we have a PM here, and since we have estimates on where the support here is, this is actually a finite dimensional problem. But it uses an uneven section of the infinite matrix. So this is for the semi-infinite dimensional problem. I'm going to go to the full infinite dimensional problem in a second. I just wanted to show you what you get as a corollary to this, because in finite dimensions, you recover exactly what Emmanuel has already discussed. So if we had a finite dimensional problem, then you'll see the log factor here, the incoherence parameter, and what you normally see. And say for the discrete Fourier transform, we know that this guy here is going to be 1. So we recover the already known results. So essentially, the results in infinite dimensions are just generalizations of the finite dimensional cases. Okay, so this is the theorem for the full infinite dimensional case, and that becomes slightly more involved. The problem on the previous in the previous theorem that is there's an m here, and that m is not sufficient for the infinite dimensional problem. You need to replace that by this theta, which looks quite horrendous, and you can also simplify this, but then it's not as sharp, but it's finite. And if you actually have n and m satisfying these conditions, you'll get recovery. And this is not going to be perfect anymore because we have, I'm just going to say that on this previous slide. Now we have y0 plus x0 plus this h guy. So we're not going to have perfect recovery, but we'll be able to bound the error in terms of the tail, the L1 norm of this here. So in particular, if we solve this problem here now, and this is the full infinite dimensional case, then actually the difference between the psi here and the original guy we would like to recover is given by this here, and it's completely controlled by the perturbation h in L1 norm. So this is exactly the case that I showed you, where we had something that was sparse and then some tail, and here that would be the tail. All right, I'm going to show you at the end now one more example on how to do this. I've taken now a phantom, and well, this is not a brain image, and I've done this deliberately. There's more to MRI than just medical MRI. So here in Cambridge we have a community that does a lot of different kinds of MRI, and they're chemists or chemical engineers, and they're interested in monitoring some kind of chemical reaction. So this could, for example, be, say, temperature or something like that. It's simply a function that I've picked, and it's simply a sum of some tensors of sine functions. And we're interested in actually recovering this guy here from its Fourier transform. That's the bottom line. So how do we recover it? Well, first of all, we're going to make it sparse. That's the whole point with this. So there is only 70 of these guys here that are non-zero, and everything for j greater than 700, everything is 0. So how would you do this in the classical MRI case? Well, we know that we can express G now in its essentially Fourier series. This should be a double sum. I just did that for simplicity. And this is the original guy. This is the classical way by truncating the Fourier series and get this. And this is the reconstruction. And the reconstruction is pretty good, right? Can you see any difference? It's hard to see, very hard to see. However, if you enlarge it, you see it. And I've picked this problem here deliberately because, so this is the original, and here you see the effect of truncating. And what I've done here, I was a little mean, should I say, to the Fourier series, because you see what I did was that I took these sine functions here, but this, can you see this? This is on 0, 1. So it's not periodic. So it's a function that is smooth everywhere, but it's not periodic. So the problem is that the Fourier series doesn't converge so quickly. So even though we get something reasonable here, when you actually enlarge it, you will see the problem with the reconstruction. Okay, we could try, the good old-fashioned finite dimensional compressed sensing idea now to try to reconstruct. The problem is that it is not sparse. So if you do L1 directly, you get complete nonsense. I didn't even implement that, or I didn't want to show you. It gives you rubbish. What you can do is that you can try total variation, just as an alternative. The problem is that that's not so good either, because total variation here, we have a function that goes something like that. So this guy here now, I've tried to reconstruct, and I've taken half of the samples, so just 50% of the samples. And you see sort of the reconstruction it's in the ballpark, right? But it is actually quite far away from perfect reconstruction in this case here. But we haven't used the original sparsity, right? The whole point is that this guy here was sparse in these sign bases. That we haven't used. So if you actually do this in this infinite dimensional way that we suggested before, we create the infinite matrix by taking the Fourier transform of these basis functions. And then we have a theorem telling us about how large should n be, where do we need to sample from, where is the important information. So in this case here, we choose n equals 15,000. And now I randomly choose a set, omega here, and the size of that is 500. So these are the observations, and we're now trying to reconstruct x0, the coefficient vector, from those observations. And I plug this into my computer, and this is what we get. You see, so this is the difference, and then you say, well, that wasn't perfect recovery, was it? Well, you have to use an iterative solver. This is the best that solver can give me. This problem here was actually done on CVX, and I can't squeeze more out of it. So we'll have to take that as sort of perfect recovery. And here is the original guy, and here is the reconstruction. And well, it's not so easy to see any difference, so we have to enlarge it. This is the original guy. This is the full sampling with the classical Shannon sampling theorem. That took us 250,000 samples to reconstruct that. This guy took us 500 samples. So not only can you dramatically subsample, but you could improve the results big time. Because what did we do? We used the sparsity in the basis that we had. That was the whole point. So essentially, the take-home message is that you can reconstruct from the same amount of data, and you can reconstruct in whatever basis you feel like. And when you do that discretization, you actually preserve the properties of the original problem. And you can do this in a linear way via the generalized sampling theorem. And you can also do this if you have sparsity or rapidly decaying coefficients with infinite dimensional compressed sensing. And with that, I thank you so much for your attention.
Okay. Questions?
What if you don't know the basis?
No, absolutely. That's a very good point. The whole idea is that there might be some reasons why you know. You have some kind of image, and there's been somebody who has been developing theory saying, well, these kinds of images or functions are going to be good for that. But it's a very good point. But consider the following. We get, n samples from the MRI machine or whatever equipment you have. And then we can choose. The theorem says that, well, we know how many samples we have. And then the theorem says, okay, how many coefficients can you reconstruct with that information? We can try different ones. But the whole idea is that there is some prior information, right? Which one is good? Which basis is good for this problem?
Again, this is a very interesting presentation. I understand this is generalization of the work that Ben Adcock presented last week.
Indeed.
And in that particular case that Ben calculated in his presentation, this approach works perfectly. I can confirm that, and I run some additional tests. And Ben was right. The condition number of the matrix flattens out, so it's perfect. And as a result of that, some internal discussions with my colleagues, the question that we have is, what about one very important, particularly important case when sampling basis is Fourier basis and reconstruction basis is curvelets? We need curvelets. We want curvelets because Fourier integral operators are sparse in curvelets. So the thing is, you provided the formula, general formula estimate for the minimum number of samples based on the number of coefficients in the reconstruction basis, basically. Do you have any analytical result for curvelets yet, or maybe you point us?
It's a
very numerical experiment, of course. But then if you have something, that would be really useful.
It's a very good question. Okay, so what we've covered so far is some wavelets. We've covered polynomials. So for example, for polynomials, the ratio is that the samples, n has to be order of k squared. K being the number of coefficients.
Exactly.
And this is sharp, we know that.
We got that, yes.
So it's a great surprise that you get linear in Haar. But what we have for arbitrary wavelets is that n is equal to order of k 2p over 2p minus 1 order, where p is the smoothness of the wavelets. But what is a great surprise is that you get linear in Haar, and Haar isn't smooth. So we don't know. We don't know if this is sharp. We actually doubt that it's sharp. But the good thing is that you can never have, so if p is 1, right, it's not going to be worse than for a polynomial case. So we strongly suggest or suspect that you'll have much nicer for all these general things. But we don't know. And we're trying to prove, and we're trying to compute. And essentially, you can ask for any kind of Emmanuel has been very heavily involved in developing all these types of nice function spaces where you can where we have rapid convergence. So yeah, it's completely open, and we're working on it.
Then OK squared, that is better than what we have now, about 1/2 k n equal to square root of m. Basically times 1/2, something like that. If it's better than that, then that will be perfect actually. We don't need to beat that actually.
Right.
That will be excellent for applications. So I guess we just need to do some numerical experimentation. Thank you.
Oh, absolutely, yes. So now right, it feels like we're sort of trying to drink from a fire hydrant. It opens up so many open questions that we can't solve, and if people have suggestions and please feel free to fill in the gaps, because there's a lot of things here. So you can essentially ask the following question. Given your Fourier coefficients, you're going to reconstruct in whatever basis, find the ratio between the samples and the coefficients you're going to reconstruct to make this stable, in any kind of. And then of course you say, well, what you see doesn't have to be Fourier coefficients, it can be coefficients in some other basis, right? So essentially the question is, there's an infinite amount of combinations you can do this, and then you want to combine this with compressed sensing and ask exactly the same questions. You need to have conditions. How far do you have to go into infinity to sample? All these things. So we don't know. I hope to be able to report on this in the future.
Thank you.
For the piecewise constant example you showed at the beginning, so this recovery technique can get the sharp edges, no gibbous phenomena?
Well, okay, so it's a good point. I mean, essentially what it says is that if you have something where the Haar wavelet is good, it will. So I'm not saying that Haar wavelet is going to cover all problems. It will be the cases where the Haar wavelet is going to be good. I can easily give you an example where it's not going to be good. But so if you're interested in recovering edges, maybe there's something else. I'm sure that Emmanuel has tons of tools in his box to cover these problems, and then maybe that is the one you want to go for. But the problem is that you see the Fourier coefficient. So you see the Fourier coefficient, and then you want to reconstruct in the other basis. So there's prior work to this. Somebody has to come up with some estimate saying, this kind of function, you're going to use this. And then I say, okay, great. And then we use this here to reconstruct the coefficients in that basis. Yeah,
the basis. Is it crucial that it's an orthonormal basis, or could it be something?
No, that's
dictionary?
Sure. No, that's a very good point. It's a very good point. Yeah, sure. It's a very good point. Okay, so we start with orthonormal basis because that's the easiest thing, right? And then you can do respaces, but that's going to have effect on the constants. We can bound and do all that stuff. And then, of course, okay, what if it's a frame? What if you have redundancy? We haven't solved that yet. We're working on it. And even more problematic is what if it's actually a basis and an ill-post problem. In fact, so what you're going to be measuring is something that you have linear functionals, but these are not going to be from some basis which is nice. So there's tons of things, and we haven't solved it yet. And the first we're working on now is how to do this with redundant functions. Yeah, that's a very good point. We don't know how to do it yet.
Okay, so thank you again.
Great. Thanks so much.